In this video, I will explain the notions of antiderivative and indefinite integral. There are two different things that we call integrals. We use very similar notation, but they mean something very different. The first one is the one we already know, the definite integral, the integral from a number a to a number b of a function f. We already learned the formal definition of it. It's quite complicated, but ultimately the definite integral is a number and it represents area geometrically. The new concept is what we are going to call indefinite integral. It's written similarly, the integral of f of x dx, but now I don't say from where to where. I don't say from a to b. And this is something new. Here's how we define it. I begin with a function f defined on an interval. We only take integrals over an interval. I'm going to say that an antiderivative of f is any other function whose derivative is f. So I give you a function f and I ask you, it's a derivative of what? Notice that I say an antiderivative, because in general there will be more than one. Every function can only have one derivative, if it has one, but it can have many antiderivatives. And the collection of all the antiderivatives is what we are going to denote with the symbols. That's what the indefinite integral means. So these two things are different. The definite integral is a number. The indefinite integral is a collection of functions. The definite integral means area, whereas the indefinite integral means antiderivative. A priori, these two things have nothing to do with each other. They are completely different and separated. But we use very similar notation, and that's because they are related. They are related by the fundamental theorem of calculus that will come in a few videos. But for now, at this level, they are two separate things. Let's see with an example how to compute this. As an example, I want to calculate the integral of x squared dx. So I want to find all the antiderivatives of the function x squared. I can guess, because this function is simple enough, and I can guess that the function 1/3 of x cubed will work, will be an antiderivative. And I can check that, because the derivative of 1/3 of x cubed is 1/3 of 3x squared, or x squared. It works. And of course, if this function works, if I add a constant, it will also work, because the derivative of a constant is 0. So for any constancy, the function 1/3 of x cubed plus c is also an antiderivative. And we are done. That's all of them. Because I recall there was a consequence of the mean value theorem that we proved in an earlier video that said that if two functions have the same derivative on an interval, then they must differ by a constant. So what that means is that once I have found one antiderivative, any other one must be the first one I found plus a constant. If we didn't have this little result, I could only say that I found a bunch of antiderivatives, but not all of them. But now I have found all of them. So in conclusion, the integral of x squared dx is 1/3 of x cubed plus c. There is a bunch of so-called integration techniques, which are methods to try to compute antiderivatives easily. But by far, the most important integration technique is guess and check, which means literally that. Make a guess for what you think the antiderivative should look like, check if it works, and modify it as necessary. I'm going to illustrate this with an example. I want to compute the integral of 2x plus 7 to the 11 with respect to x. So I'm looking for a function whose derivative is this, 2x plus 7 to the 11. Well, since I know the power rule, this makes me think of the 12th power of 2x plus 7, because I know the derivative will be similar to this. And I know it's not going to work exactly, but hopefully we'll come close and then I can fix it. So I will begin by trying 2x plus 7 to the 12th. And its derivative is 12 times 2x plus 7 to the 11 times 2, chain rule, or 24 to x plus 7 to the 11. So it's the function I wanted, but with an extra 24. I can fix that. If I take the function I tried and I divide it by that 24, that will work, because now the derivative is 124 times 24 to x plus 7 to the 11, or 2x plus 7 to the 11. It worked. So I found a function whose derivative is what I wanted, and therefore the integral of 2x plus 7 to the 11 dx is 1/24 to x plus 7 to the 12 plus c. We're done. This method, even though it seems very rudimentary, is very powerful, and there are a lot of functions whose antiderivatives you can compute this way. In fact, all the integration techniques you will learn, substitution, integration by parts, and so on, are just sophisticated guessing and checking that make the guessing part easier. Now is your turn. Now you try it. Here is a collection of antiderivatives that I have chosen that you can solve entirely by guess and check. You don't have to use anything else more sophisticated. Just guess and check will do. At this moment, if you were reading a calculus textbook, you would probably be presented with a table of elementary antiderivatives, which is a bunch of formulas. But my point is that you don't need those formulas. If you know the differentiation rules, you understand what an antiderivative is, and you are comfortable with guess and check, you can solve all these questions without having to memorize anything new. And isn't that a much better way of doing it? So I urge you to try to solve these questions without looking up anything. And the nice thing is that since you can check your answers by taking their derivatives, you will know whether they are right or not.